Hey Taylor,
Hey Freddie, how's it going?
it's going all right. How are you?
Yeah, doing all right. Doing all right. Spent most of the weekend grading exams. It was not fun, especially.
Sorry.
Yeah, it's not your fault, but especially the fallout after that when the students saw their grades.
Uh-huh. Did it
Yeah,
not go very well?
yeah, it didn't go very well. I think the average was like between 43 and 47 for almost both sections out of 100. So
Really?
yeah,
Was
yeah.
it
I mean,
do you, do you think like the either the exam was particularly hard or you grade particularly hard?
I'm not sure of the first, but I do grade. They need a lot of justification for their work. But I made that clear from like the quizzes we do in class.
Yeah.
But yeah, so I thought I made it clear enough, but I don't know. I think some of the questions were hard too. I think some questions were hard. Like there were word problems that they maybe didn't know how to do.
So
Um,
the average was below half the points? Wow.
yeah, yeah, yeah. I mean, like it's
Really?
distributed pretty wildly though. I mean, like in general, like
Yeah.
the highest scores were like I think 80s for both sections.
Cool.
Um, yeah, and most of the grades were like, yeah, it's still not that good. It was like around 50 to 60, but they had some bad ones on the side.
Yeah, yeah.
Yeah. So I'll have to see what I do next. Hello, hello, Paco Manzelos. How y'all doing?
Pretty good. How about you?
Doing all right. I just submitted my first solo paper yesterday.
Nice.
Yeah, it's a little confusing though. Sometimes they ask for like a cover letter, and I don't really know what a cover letter was, and they're like different article formats they wanted. It's a little confusing, but
Yes, I did it too, and I just did some random, something random, and it wasn't nothing they care actually.
yeah, I figured like they wouldn't like say we're not accepting this paper because you didn't include your address in the cover letter or something stupid like that. I figured like they would just read the PDF I sent them. Yeah. So now we're playing the waiting game, right? We just wait and see.
I think on average it takes about 7 months.
I think so. I saw also they said like they would expedite the review process for grad students as well.
Oh,
Sometimes they have that like in some journals. I didn't see
yeah.
the option
So
for that one.
I know that Journal of Number Theory does that.
That's why I submitted too.
Oh, I see.
Yeah,
But I'm
that's
not
funny.
sure how honest they are because I did the same thing. I have submitted my paper on January 6th, and I have no news so far. So
Mm-hmm.
while on the other hand, submitted another paper to another journal and it's now accepted. So within a
Oh wow,
month.
that's the same time you submitted both of them.
Yes, yes.
Oh wow, that's a big difference.
And the other ones say that they have like a 7 month waiting period, at least 7 months.
So you got
I
really
guess I was just
fast.
lucky, yes.
Yeah, they really liked it. Nice.
Or I
What
was
was
just lucky. I think they might needed some papers to move to specific. I don't know. Like
I see. What was the journal, if you don't mind me asking?
yes, it was the transactions of the AMS,
Oh, nice. Very cool. Which paper was this? Was this the one you
the,
gave a
the
talk on?
classic conjecture. Yes,
Yeah. Oh, cool. Nice. Very nice.
All right. Hello, everybody. Sorry I'm late. I guess I'm a little discombobulated. I had a Zoom midterm this morning. Didn't go terribly, but I guess it took some energy. Yeah, I just spent the last like 2 minutes looking for the camera icon on my desktop, and it was there. I don't have that many icons on my desktop, so I'm not sure exactly what the problem was. But... All right. And I think I actually forgot to upload the Friday, whatever fraction of a lecture that we had to Zoom. So I will do that. I'll upload that lecture and this lecture at the same time. But yeah, are there any questions? Yes, I was looking, this could be, I think this is going to end up being a little bit of a shorter lecture, actually, which should be fine. So I want to make some remarks, kind of brief remarks on chapter 4, which is profinite cohomology. It's a very important topic, but it's kind of just like a bunch of minor variations on stuff that we've already done. And so I'll state how it goes, and then, the details, you really can look at them as you like. And then for some reason, there's this short chapter 5. I was kind of expecting chapter 5 to be like Galois cohomology finally in earnest, but it isn't. Chapter 5 is a chapter on cohomological dimension of a profile. We already talked about the cohomological dimension of a discrete group, although that was not in the textbook. And this is a suitable profinite analog of it. I mean, it's fine. It seems strange for there to be a whole chapter about it. So we'll see. I probably will have time to say very little about it today. But I wanted to point out that this could be a very plausible and not terribly ambitious topic for a Friday lecture. So if somebody wanted to just look at chapter 5 and cover, what's in chapter 5 of the text, like this Friday, for instance, would be the right time. And I mean, you can check. It's really, I mean, it's nice material. I certainly learned it from Sayre's book, Galois cohomology, as well. I mean, he has more in there than is done in this book. But it's really just a few pages of pretty nothing too crazy is happening there. Okay. Anyone feel like they might want to do that? Do a Friday lecture on this short chapter 5 of Harari's book? People are not jumping on it. Well, we'll see. All right. I mean, it doesn't have to be this Friday. This Friday would be, would be nice. But anyway, all right. Well, let's get on with things then. It seems like that's what we're supposed to be doing. Yeah, somebody should take pity on me and explain to me how you set up ELC to receive assignments, because I tried to do it over the weekend and it didn't really seem to work. But I also had trouble, like, I asked students to let me know if it worked, and like only one student wrote back to me and he was like, it doesn't work, but then it often doesn't work when I try to upload assignments to ELC. And I was like, wow, what's up with that? Anyway, so it didn't seem particularly complicated, but there were just a bunch of options, and so maybe I didn't check the right thing. Anyway, all right, let's get into it. So so we want a suitable analog of group cohomology for a profinite group acting on certain Z modules. Okay, and so the question is kind of, let me check the size of this. It seems about right. Right. Okay. And so, yeah, so that's our task. So the task is how do we what is the right category? We know, so we have a profinite group, which is a group equipped with a topology in which it is compact and totally disconnected. Equivalently, it's an inverse limit of finite groups, but so somehow the specific inverse system is not really part of the data, although just as soon as I said that, you could take the inverse system to be the system of quotients by finite index open normal subgroups. Anyway, so we have this topological group of a very nice form, and the question is, what should its cohomology be? Right, or what should the category of modules be? And so, well, I mean, of course, we don't have to say anything at all. We are, unlike Harari, we did define G modules for a totally arbitrary group, right? So why are we doing anything? You could ask, why don't I just take the category of G modules as we had before? So that doesn't work, and I'm not going to explain exactly why it doesn't work, but I'll just point out a simpler analogy, which should make you sort of not surprised that it doesn't work. Okay, so for instance, if you compare a simpler thing, if you have a field, you have the absolute Galois group, which I will denote by little g sub k of the field, so the automorphism of a separable closure of the group. The automorphism group of separable closures of the group that fix the field that fix elements. Sorry, I'm a little out of it for some reason, which fix elements of the field pointwise. And so the idea is that just as a group, the way that field automorphisms acting on algebraic extensions work. Not for the first time, I'm pointing out that the automorphism group of any algebraic Galois extension of fields is just the inverse limit of the automorphisms of the finite Galois subextensions. Okay, essentially this is because any automorphism of an algebraic field extension acts with finite orbits, and so therefore, if you know what your automorphism is, it restricts to an automorphism on every finite Galois subextension. And if you know the automorphism on each of those finite Galois subextensions, then of course you know the automorphism on the entire field. Okay, so it has this structure, right? And so again, it maybe looks sort of fancy or confusing or whatever the first time you see this, but this defines a certain topology called the Krull topology on the Galois group, namely the topology of just this profinite topology, right? And it makes it into a compact, totally disconnected topological group. Why are we doing that? Well, for instance, if you want to retain the correct Galois correspondence between subextensions of K sep over K and subgroups of the absolute Galois group, the correct statement of the infinite algebraic Galois correspondence is via closed subgroups of the absolute Galois group. Okay. Which is not the super deepest fact. Well, here may be the fact that every closed subgroup of a profinite group is the intersection of the open subgroups that it contains. That kind of makes more sense on the Galois theory side. On the Galois theory side, that's saying that every algebraic Galois extension is the union of the finite degree Galois subextensions of it. So sure. Also true if you don't say Galois. Anyway, so the idea here is that you're not going to get the Galois correspondence the way that you want it to from the finite case if you ignore the topology. You kind of have two choices. If you have this group that is arisen as an inverse limit of finite groups, you should either take seriously the topology and do things correctly with respect to the topology, or you should just kind of take limits from the finite case. That's your other choice. But you shouldn't. You have to do one of those things. You can't just say, all right, well, I just have a group and I don't care that I have a topology in the group. Yes, you do care. Okay. So again, otherwise put, this is coming later. When we want to, we are going to want to just kind of, in profinite cohomology, we're going to want to realize profinite cohomology as a limit from the finite case. Okay, so you could try to do the following. So for any topological group G, you could consider the category. This is not the actual category that I want, even if the group is profinite. So I'm putting a tilde on it to distinguish from what the CG will actually turn out to be. So this first attempt would just be, okay, like let's have your Z module have a topology as well. Okay, so you consider topological G modules. So what does that mean? It's a topological commutative group. It still has a Z-linear action. But now that I have topologies on both G and M, I can require this action map to be continuous. Okay, so that's a certain category. And that's very interesting. You get to ask yourself all kinds of questions. You ask yourself, is this an abelian category? Is taking the invariance a left exact functor? Does it have enough injective objects? Okay, so if the answer to all those questions turns out to be yes, well, then you can define the cohomology groups as the derived functors, the right derived functors of the left exact invariance functor, if all that is true. And then you get to ask a fourth question is, you can also define a notion of continuous cochains, okay, so where you take exactly the same definition of cochains, maps from some number of copies of the group into the module, but whereas you require those maps to be continuous. Okay, and so what I'm saying is that you could ask this question, for any topological group, and it's a natural question. It doesn't work out that well, though, is the answer. So again, I'm not going to stop and do this. It is kind of interesting, but it doesn't. It's kind of the opposite of what we need to do. It works out much better in the profinite case than in the general case. And I don't even remember everything I used to know about all the answers, but I'm prepared to guarantee to you that the answers to these questions are not all yes in general. So people have tried. I found a 2008 paper of Matthias Flach, the Caltech mathematician. So he takes, following Grothendieck, SGA something or other, he takes a more categorical approach to the cohomology of topological groups, and it has some interesting I won't explain what that is. We don't need it. One thing, just as you could take a topological approach to group cohomology, which we waved our hands at, right? You could define group cohomology as cohomology of the Eilenberg-MacLane space of the group, right? We mentioned that at least, although to do that in full generality, you would have to understand what is like the topological structure that corresponds to a G module, right? So we really only talked about the Eilenberg-MacLane space, where the coefficient is which is just ordinary integer coefficients. But it turns out, this works really well. If you have, maybe I think I said this, I didn't say much about it. If you have a group acting on, if you have a G module M, then on the topological side that corresponds to something called a local system on the Eilenberg-MacLane space, which is very much like a sheaf of a certain kind. Okay, it is a sheaf of a certain kind. Anyway, so you could do that. And then if you have a topological group, there's something called a classifying space, which is a general, which when the group is discrete is just the Eilenberg-MacLane space. So this is classifying principal G bundles on topological spaces. And okay, this is not actually an algebraic topology course. Maybe it should be. Probably it shouldn't be, but maybe it should be. But it's not. So you get an interpretation via this classifying space, the topological group, which is of interest to topologists of various kinds. So that comes up, and then he does. So anyway, so he discusses these things. If you do it in a different way, then it's related to things like the classifying space, and in certain situations, it's related to the continuous cochains. But anyway, so it doesn't work out in full generality. Right. So things work much more nicely when the group is profinite. So let's restrict to that case. In this case, we're still not going to do the CG tilde that I mentioned before. We're going to restrict. We're not going to take just any old topological G module. We're going to take a very particular kind of topological G module. Just as a reminder, this theory is actually due to Tate. So this theory of cohomology of profinite groups, okay. Unpublished, as for many of Tate's best works. Okay, so what do we do? What is the actual CG rather than CG tilde? We only consider discrete G modules. Okay, so on the one hand, first of all, that literally just means that my, the topology on my G module is the discrete topology. And now you say, well, what are you doing? Any G module would have, you could always put the discrete topology on it. How is that the same than not having any topology at all? Well, first we put the discrete topology on it, but then we require that the action of G on M, the Z-linear action, which is giving us the module structure, is continuous. Okay, and so if a topological group acts continuously on a discrete space, that's a quite strong condition. Actually, that's certainly not automatic. Okay. A discrete group would act continuously on anything, but a non-discrete group acting continuously is like the most stringent type of condition. And so yeah, I just did a couple of exercises to understand that. So indeed, what does it mean for any topological group to act continuously on a discrete G module? It means that all the point stabilizers should be open subgroups in G. Okay, I mean, this is literally just an exercise in this is the product topology, and it's just a general topology exercise. Okay, so that's a strong condition that the stabilizers are open. Okay, as I said, if the group was discrete, then everything would be open. So that then of course it wouldn't be a condition, but in general that's a strong condition. And so for a profinite group, we know that every open subgroup has finite index, and so right, so for a profinite group to act continuously on a G module M, that means that M is the union of its invariants under open, hence finite index subgroups of G. Okay, so every element Y, just because every element has to be the stabilizer of every element has to be open in G, and so every element has to be acted trivially upon by an open, hence finite index subgroup. And then just so that's true. And then, as is often the case, you can just insert the word normal if you want. If I have any finite index subgroup, I just intersect what's called the normal core. In general, it's just the intersection over all the conjugates. That makes sense for any group. It's the largest normal subgroup contained in a given subgroup. Okay, normal core. It's a natural thing in group theory, whether you've seen it or not. And so if your subgroup has finite index, then a one-line argument shows you that its normal core still has finite index. And if you're open in a topological group, then all of your conjugates are also going to be open, and your normal core is going to be a finite intersection of open subgroups, and so it is again going to be open. Okay, so passing from open to open and normal is fine. Okay, and so this is a very strong condition. This is, I think I'll say a little bit more about this. Even if G were a Galois group, if you apply this on the field theory side, you'll see what it'll become a kind of familiar statement. Okay, so that's a strong condition on M. It means that sort of locally G is acting through a finite quotient. That's the idea. Okay, right. So in particular, any continuous action of a profinite group on a discrete module has finite orbits. That's what I was just saying, right? So if you act on a particular element, then since just by the orbit stabilizer theorem, right? If the stabilizer has finite index, then the orbit is G modulo the stabilizer, which is finite. That's what finite index means. Okay, so the action is kind of locally finite. Okay, so I'm not saying there need not be a finite index subgroup of the group. What am I trying to say? The entire action doesn't have to factor through a finite quotient of G. It may or may not, but if you look at the action on any particular point, then its orbit will factor through a finite quotient. Okay. Right. And so yeah. So what am I saying here? So in particular, to say that your profinite group acts continuously implies that it has finite orbits. Again, for a second, it might sound like the converse should be true. But again, the problem is that, again, by orbit stabilizer, to say that the orbit is finite is the same as saying, certainly the same as saying that the point stabilizers have finite index, but I want the point stabilizers to be open of finite index. And again, unless my group is strongly complete, which we talked about on Friday, it's a pitfall. Every open subgroup has finite index, but in general, not every finite index subgroup is open. Although that is true if the profinite group is topologically finitely generated. Okay, so anyway, so in general, continuous implies that it acts through finite orbits. Okay, yeah. So here's an exercise, very important exercise, looking forward to what's coming. Yeah. So suppose I have a field, and suppose I have the absolute Galois group of the field. I mean, by the way, again, by the exercise that I stated, I guess at the beginning of the course, it'd be great if somebody solved that, by the way, it's a fun exercise. Every profinite group is isomorphic as a topological group to the Galois group of some algebraic field extension. And so when I define profinite cohomology, not every profinite group is given to you as a Galois group, but it could be. Okay, so the idea is that, like, oh, let's take G to be the Galois group of a field. It's not actually a special case. I mean, it's the general case if you want it to be. All right. Okay, so you take your Galois group, every profinite, okay, except here I could have made it. Every profinite group is a Galois group. I'm not saying that every profinite group is the absolute Galois group. That's a further restriction. Okay. In fact, it's a very interesting question to ask: which profinite groups can be the absolute Galois group of a field? Remind me to talk about that at some point when we have further time. Secretly in my mind, I think about that as being like the real inverse Galois problem. So which groups are absolute Galois groups. Okay, so right, what's this exercise? You've probably read it by now. So you take a variety over a field, you've probably seen this before, then the absolute Galois group acts on the separable points. Okay, yeah, and so by the way, yeah, maybe I should say you could do this whole thing, now I kind of regret it a little bit, you could do this whole exercise for any Galois extension L over K, any Galois extension. It doesn't have to be the whole thing. So maybe go back and do the exercise with that further generality. Yeah. So I guess what I'm saying is that in general, if I had a variety that was defined over a field K, and then L over K was a Galois extension, algebraic, but possibly of infinite degree, then the Galois group of L over K would act on the L value points. I'm sure you've seen that before. Hope you've seen that before in one context or another. But for instance, if you embed your variety into projective space, or even locally, you do that. Maybe you locally embed your variety into affine space, and then literally it's just acting on the coordinates. So it's nothing. You can say it more scheme theoretically if you want to, but it totally agrees with the most naive notion of actions. Okay, and so here's the point. If you give the set of the K set valued points, or again more generally the L valued points, if you like, if you give that the discrete topology, then the action is continuous. Okay, this is not a profound exercise. This is sort of explaining. This is again, it's coming from this property that I said before that yeah, I'll let you untangle it. So it's not a tough exercise, but it's an important one. This is the way that it's really a property of the way the automorphism group of L over K acts on L, and then everything else comes from that property. And then you might want to be more scheme theoretic about this, and you can, but you should be a little bit careful. So what's a variety? Like what pleasant adjectives am I including, and what pleasant adjectives am I not including? It's not always completely standard, right? I didn't say it was nice, I just said it was a variety. In fact, all you really need, any finite type scheme, the result would still be true, okay? And then, but you actually do need finite type. So if you could have an infinite type scheme where the action on the action on the K set points is not continuous in this way. Okay, so that's a good, I think, pretty sure. Okay, so that's a good exercise. So anyway, this is very important. So this is sort of like why is this an interesting this condition of being continuous for the discrete topology? It looks really strong, and it is strong, but it arises in nature because of this example. Okay. This is not fully an example because I don't have a this is an example of the right thing topologically. This is not yet a z-linear action. To get to get an honest element of my category, I shouldn't just take a variety. I should take a commutative group scheme. And then you're in business. Okay. All right. So just give you some facts here. So again, I'm not going through this. I'm just telling you kind of how it goes. So let's take a profinite group. So then this category. So again, G modules, which are when viewed as being discrete, the action is continuous, which again means that the point stabilizers are open. So it's a wonderful category. Well, it's a pretty good category, very good category. It's an abelian category. It does have enough injective objects. That's not obvious. It's proven in chapter 4 of Harari. Here's the one cloud in the sky. If the group is infinite, then it doesn't necessarily have enough projective objects. Okay, so that's again, I haven't looked into this, but I would if I had to make a guess, I would guess that if G is infinite, then the category never has enough projective objects. Okay, and so what's going on here? This is kind of familiar, maybe. This is This is analogous to the fact that if you take a topological space, then the category of just abelian sheaves of Z modules on that space always has enough injective objects. That's a foundational result when you're studying sheaf cohomology. They don't say that the category of sheaves on a topological space has enough projective objects, and it very, very rarely does. Like, in fact, in the early days of Math Overflow, I had there was some dinner with some seminar speaker out at the 5 and 10, and one of the algebraic geometers was in the department, and he was asking this question. He's like, when are there enough projective objects in the category? And I was like, oh, I don't know. That's a really interesting question. And again, it was like Math Overflow was like 3 months old or something at this point. And so I went on Math Overflow the next day, and I was like, so-and-so like wants to ask, like, you know, or not like this question, you know, I attribute this question to my colleague in the department. And then within like a day or two, a Math Overflow user named VA answered the question. You know, so gave a pretty good answer to the question. That may or may not have been the same person who asked me the question in the first place. So perhaps I misunderstood, and it was like a, you know, it was like a riddle or something. Maybe it wasn't. Maybe it wasn't like a sincere question. Anyway, so it's a weird condition on a topological space for the category of sheaves of abelian groups to have enough projective objects. That doesn't happen. Okay, so that doesn't happen here. And so why is that bad? Well, we use that, right? We used the fact that our cohomology groups were X groups over the group ring, right? And so X is a bifunctor. So X takes 2 arguments. It was X'd from Z into M, right? Z with trivial action. And so in order to compute your X functor, you could either take a projective resolution of Z, right, and then hit it with the Hom, and then, or you could take an injective resolution of M. And we've done sort of some of both, but like the way that we derived our standard complex and the fact that that computes the cohomology, we went via a projective resolution of Z. So it's a little bit sad that that there's not necessarily a projective resolution of Z in this category. Okay. What was I thinking? Oh yeah. So by the way, like, how do we know that Z is in this category? But just as a not really too insulting to be an exercise. If you take any Z module and you let any profinite group act trivially on it, well, then all the stabilizers will be the whole thing. So every trivial Z module lives in this category. Okay, so yeah, so one of the instances here is that it makes you wonder whether cochains will compute the cohomology. Anyway, so the functor is left exact. So I have a left exact functor, I have enough injectives, and so the cohomological business kicks in just fine, right? So I get this cohomological delta functor, and that gives me these cohomology groups. And you see by that nobody cares, but the notation, technically I'm abusing notation here, right? Harari is, maybe now I finally see. So Harari is not abusing notation, but I am, because I've already defined this thing for any group G, whether finite or infinite. And this is, everything is continuous now. So technically I should do like a sub C or something to indicate that I now have topologies in play, but I won't. We'll just understand that we're going to be working with profinite groups. Okay. Yeah. So here's another little exercise getting you ready to do cochains and some other things. Yeah, so if I have a function from a topological space to a discrete topological space, again, this is the situation where we had like an action. So an action on a discrete module M was a function from G cross M to M. So maybe we should have had this exercise before. It's very easy for a function out of a discrete space to be continuous. They're all continuous. It's very hard for a function into a discrete space to be continuous because there are so many damn open subsets. All of their inverse images have to be open. This again, this is pretty obvious if you've been thinking about topology, recently at least. So a continuous function into a discrete space, a function is continuous into a discrete space if and only if it's locally constant. So if and only if, well, the fibers of the map have to be open sets by definition of the discrete topology, and that's the proof. That's what it means for a function to be locally constant. So that's kind of obvious. Moreover, if the space is profinite, if the domain is profinite and the space is discrete, then the continuous map has to have finite image. Why is that? Because I'm taking a even compact space and I'm partitioning it into finitely many open fibers, so that the number of fibers should be finite if it's compact. And so then if I have a profinite group and a continuous function into a discrete set, then every continuous function does factor through a finite quotient. So that's, again, what we were doing before was not exactly this, right? Because we had an action. We were looking at maps from G cross M to M. So that's actually slightly more complicated. But at the level of space, again, this is a pretty easy exercise that they all factor through some open normal subgroup. And so you can, right. And so therefore you get this very important fact that the ability to pass to the limit is just kind of built into the topology here. So here I am doing a sub C. So by Hom sub C, I just mean the category top where the maps are continuous functions. So the continuous functions from a profinite group into a discrete space, these are, okay, but every profinite group is equal to this inverse limit. And so what we're deducing here is that this Hom functor is continuous in the sense that you can pull the limit out. But again, you have to be a little bit careful here. So in general, Hom is kind of covariant in its second argument and contravariant in its first argument. You're welcome to stop and think about this every single time, but you would expect, if you just think about it for a while, you would, I mean, here we thought about it. You would expect that the limit to flip around, okay? And so I claim that if you just think about this not very difficult exercise, then you're gonna get this identity that the Hom of this inverse limit of groups into a discrete space Y is the direct limit of the Homs on the finite quotient. Okay, so you see it's kind of built into profinite groups that you should be able to pass to the limit from finite groups. Okay, so now let me introduce the continuous cochains. Okay, so here I am doing a sub C just to, I'll probably forget it later, but just so before cochains were just these are inhomogeneous cochains. Okay, so we had homogeneous cochains and inhomogeneous cochains, and homogeneous had one more copy of the group, but they had to be G invariant, right? And then just by taking a G module isomorphism, we rewrote it in terms of inhomogeneous cochains. So that's what we're doing here. You could also do homogeneous cochains if you wanted. And so it's exactly the same definition. The only difference is this little sub C. Okay. And now you see though that now this exercise is starting to sound, like it could mean something, because if G is profinite, well then any product of G, certainly a finite product, is going to be profinite again. And this is a discrete guy. So again, each one of these, any individual cochain is going to factor through a finite quotient. Okay. So we define the coboundary maps exactly as we did before. So I won't even, I don't need to get my hands dirty. So I'm not even going to remind you what the formula is. It was a nice formula in the homogeneous case, and then we adjusted it to get a formula, not so bad, but a little bit weirder looking formula in the inhomogeneous case. Okay, and so now we have a very important theorem. And so the first theorem, whose proof I'm skipping, is that the continuous cochain complex does compute the cohomology. So what do I mean? I mean, it's a complex that was defined in terms of continuous guys, but in particular, it is still a cochain complex. So literally, its cohomology gives you something, and so the cohomology the nth cohomology of this cochain complex, kernel mod image, is equal to the nth cohomology group of the profinite group acting on the discrete module in the derived functor sense. Okay, so, and again, this is a little bit more interesting because we can't prove this via a projective resolution of Z. Okay, so it's a little bit more interesting that this is still true based upon the one limitation that I told you, but it is still true. So that's great. So now we have, this was like the dream. This is the thing that you might, if you see this, then you think, oh, well, maybe this is true for any topological group, like blah, 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 blah. Hell no. So this is true, but maybe it's true because like underneath the hood, something even more basic is true. So at the moment, what have we done? We have our cohomology of profinite groups is defined via derived functors of the left exact functor taking the invariance, and it's computed via continuous cochains. But what was the last thing that we said we kind of wanted to do for profinite groups? If you have a profinite group, then what would you like to be able to do in terms of computing with it? We would like to be able to view everything as passage to the limit from the finite case. Okay, just like for the Galois correspondence, it was passage to the limit from the finite case. So that's true as well. And again, maybe that truth has something to do with why this is true. I think it does. But so here it is. So these are results from Harari. I've changed the order a little bit, but all of these results are stated and proved. Occasionally, I would have wanted more details than he gave, but I guess I can be picky. Anyway, so here's the theorem. This is actually quite a general passage to the limit theorem. So we're gonna have to parse this for a little while. So first of all, we start with a directed set. So I haven't been super explicit about this, but in theory, whenever you take an inverse limit, the data of an inverse limit is a directed set. Okay, so what's a directed set? First of all, the set is, as a structure, it's a partially ordered set. Okay, but it's not just any old partially ordered set. It's a partially ordered set where whenever you have two elements, it may not be totally ordered. So neither I nor J needs to be less than or equal to the other. But the definition of being directed is that for any two elements, there's always a third element, which is greater than or equal to both of them. Okay, so that's what a directed set is. And so, that is what am I trying to say? What is the correct formalism to take either a direct limit or an inverse limit? The formalism is via directed set. Okay, so if you have a directed set, you can define a directed system of sets. Okay, so for each element of the directed set, you have a set, and then whenever I is less than or equal to j, you have a morphism from the ith guy to the jth guy. That's a directed system, kind of in any category. You can consider a directed system, or you can consider an inverse system, which is the opposite. We still have a class of objects indexed by this directed set, but what makes it inverse is that whenever you have I less than or equal to j, your morphism goes back in the other direction. Okay. And so again, if you have a profinite group, then the directed set is going to be the set of open, hence finite index subgroups, partially ordered by reverse inclusion. Okay. Anyway, so suppose that we have, first of all, an inverse system of profinite groups, okay, with continuous transition maps. Again, this theorem is quite general. It's pretty impressive. So most often when you have these projection maps in an inverse system, and in practice they're often surjective. Okay, and that would sort of simplifies things. But here he's not assuming that they're surjective. So okay, that's only a better theorem. Then on the other hand, we have a directed system of Z modules. Okay, or sorry, a direct system of Z modules. Okay. So again, for each I and I, you have a Z module Mi, but now when I is less than or equal to J, you have a Z module map from Mi into Mj. Okay, moreover, for each fixed I, mi is a discrete GI module. And now there's a compatibility condition that he doesn't spell out. So I decided I would spell out, even though it's a little bit confusing. So, or not. But so what's the compatibility here? So I have an I less than or equal to j. And so now I have this action. And then here I should be putting like an I here. I have this action, but I guess, yeah, maybe I should put in one more map if I can do it correctly. So right. So we have a map here, right? This map is just the projection map across the identity. Okay, so right, and that's what this is. So this map, this horizontal map here is what you get by taking the action of GI on MI and then pulling it back to give you an action of GJ on MI. Okay. And then we also have an action of GJ on MJ. And we have a map from MI into MJ. And so if you stop and think about it for a second, it makes sense for these two actions to be compatible. So the way that GJ acts on MI here, giving an element of MI, is compatible with if I embed GJ cross MI into GJ cross MJ, and I embed MI into MJ. Okay, so maybe I'm just saying too many words, but so this action here, so this is the way that GJ acts on MI by pushing GJ back into GI and letting it act on XI. And that's the same way that GJ itself acts if you include, well, it's not necessarily an injection, if you map from MI back into MJ. Okay. I don't know if that was helpful or not, but there is a compatibility condition here, and if you write it down carefully, you can understand. And so then there's just a really nice result. The nice result is that you have it's a kind of continuous function of two variables in this sense. So for all q greater than or equal to 0, you take the profinite cohomology of the inverse limit applied to the direct limit. First of all, you sort of, I guess you have to convince yourself that the direct limit of the MIs is a discrete module for the inverse limit of the GIs. That's kind of the least of your worries. And so then it turns out that you can pull out all the limits. Okay, again, this inverse limit gets pulled out as a direct limit, as I was implying before. I guess maybe I was doing like a 0 case of that before. You expect that because HOM is contravariant in the first argument. HOM is also covariant in the second argument, so it's natural to see a direct limit here that gets pulled out as a direct limit. Okay, so this is a very nice result. Okay, so this is kind of you know, maybe let's call it just let's I like to give results fun names sometimes. Let's call this the continuity here. And let's try to spell it correctly. Continuity theorem for profinite cohomology. Okay, so this theorem is saying that really, I mean, it's more general than that, right? Because I'm not even saying that GI is finite, but it could be, you know, so it's even more general. But in particular, it's saying that all profinite cohomology can be viewed as a direct limit of cohomology of finite groups. That's probably, yeah, that's the next corollary here. So if I take a discrete G module, then in particular, just taking the natural inverse system attached to my profinite group G, it's again the system of open finite index normal subgroups directed under reverse inclusion, then yeah, so again, you could really start here if you wanted. I think, you know, in my course a year ago, I sped through some cohomology groups at the end, and I think I just defined this to be the cohomology of Galois. You know, I defined Galois cohomology this way, and we were just off to the races or whatever. So you could take this to be your definition of profinite cohomology if you want. Okay, so yeah, so the profinite cohomology comes as a direct limit here. And now just the important thing to realize is that as U is ranging over open normal subgroups of G, G mod U is ranging over finite groups. And so if U1 is a smaller finite index subgroup contained inside a larger finite index subgroup, then each of these are quotients of G, but the second one is more of a quotient. The second one is a quotient of the first one. And so again, we have this contravariant functoriality. So we get a map from, am I saying this right? Yeah. So I guess the only thing that's troubling, and I'm being really, really picky here, but psychologically, I like this. I mean, who cares that one of them is called 1 and one of them is called 2? But in terms of this like inverse system, the 2 is kind of bigger in the order under reverse inclusion, right? So that's what I'm saying. So this is the where bigger literally means smaller, but that's the right way to think about it. So my set, again, my directed set is ordered under reverse inclusion. Okay. And so if I have this type of map, then my inflation map is going to take me from cohomology of the group G mod U1 to cohomology of the larger finite group G mod U2. Okay, I just keep going over the direct limit. I get the profinite cohomology. Okay, so you see that in principle, profinite cohomology reduces to cohomology of finite groups, and just take the limit. All right, yeah, so in practice, this is a good definition of profinite cohomology. And now let me write out the special case, which is, not, I mean, it's not a special case in some technical sense, but in practice, maybe you have a profinite group that, sure, it's isomorphic to the Galois group of something, but it's not given to you that way. Right, so, but let's do the special case. So let's take a field K, let's take the absolute Galois group of the field, and let's really push the analogy. So for any discrete GK module A and any finite Galois extension L over K, I'm going to write A of L as though this were some kind of thing where I could plug in the L valued points, but it's just formal. What do I mean by A of L? I mean the guys that are invariant under the finite index open subgroup GL. Okay, so if A actually happened to be a commutative K group scheme, then this would be exactly right, but otherwise it's just notation. Okay, so by A of L, I'm just writing notation for invariance under the finite index subgroup, and then you do this, and then you see that in this case, what we're saying is that the cohomology, the Galois cohomology, the cohomology in the Galois group of, and again, A is not a scheme or anything yet. It really is just a discrete GK module, and it comes out to be this limit of finite limit over cohomology groups of the finite Galois subextensions. Okay, that's very important. This is like maybe the most important thing. The most basic thing that we've said like so far in the entire course, that this is so the Galois cohomology is coming out that way. And again, you don't have to take the full absolute Galois group. You could have taken any infinite degree algebraic Galois extension, and the exact same thing holds. This is just kind of every other Galois extension is going to be determined from this one somehow. So, okay. All right, and so then let's see how we're doing here. Yeah, maybe I will just I tacked on a little bit on cohomological dimension at the end, but maybe I won't spoil it for whoever I will later persuade to give this extra lecture. So I'd be happy to end here. So just a couple of really important corollaries straight out of the book. So yeah, so I wasn't really emphasizing I was emphasizing the continuity in G, but there is also a continuity in A, and that's useful in itself. And so, for instance, every module over every ring whatsoever is the direct limit of its finitely generated submodules. If you just if you've never heard those words in that same order, then you stop and you think about it, but it's just true. It's just the way direct limits work. Okay, and so here in particular, I could take this. I don't like that. I like finitely generated, right? Because that doesn't make sense. It should be like a finitely generated ZG submodule. Yeah, okay. Right, I mean, it's gotta be a G submodule, or it doesn't make any sense. Yeah, okay. So it's the limit of finitely generated. Actually, now I'm slightly confused. Let me just quickly check. I feel like I got suckered here. Let me see what he actually says. Where does he say that? Finite type sub G modules. Okay. So you take finitely many elements and you take the G module generated by that, ZG module generated by. Okay, good. Yeah, so that's helpful. And then, right, and then moreover, this is also very important. All of the higher Galois cohomology groups, or excuse me, profinite cohomology groups, comes to the same thing, are torsion Z modules. Okay, that's very important. We saw this previously for finite groups, right? And okay, that's why we're going to get it, right? So therefore, every Galois cohomology group is a direct limit of group cohomology for finite groups. And again, by this, like, because co-restriction followed by restriction with respect to a finite index subgroup, the composition is multiplication by the index of the subgroup on cohomology. Therefore, these guys are index of U and G torsion, okay? And I can't really, okay, whatever. So therefore they're torsion. And so a direct limit of torsion Z modules is a torsion Z module. And if you think about it, you don't really get a stronger statement out of that. Like at each level, you get like a stronger statement as to like what the torsion Z module is annihilated by. But then, I mean, it depends on the group. I mean, you could, I guess you could say, let me stop and think for a second. Do I want to say more? Yeah, so you could make a stronger statement. So for instance, I skipped this. I got to skip stuff. So there's a notion of like a supernatural order of a profinite group. I'll just say it, I guess. So what do you do? So for every prime number P, and I have a profinite group, I am going to attach a non-negative integer or infinity to that prime number P. And I'm going to call that like the supernatural order at P of the profinite group, which are equivalently the supernatural order of the CeLO P subgroup of that profinite group. So what do? I just look at all finite quotients of my profinite group by open subgroups, and I look at the largest power of P that I get in any finite quotient. So, if P doesn't divide any finite quotient, then the supernatural order at P is P to the 0. If P divides some finite quotient, if P cubed divides some finite quotient, but there's never any finite quotient which is more divisible by P than P cubed, then the supernatural order at P is P cubed. If, on the other hand, for every n, there's some finite quotient which is divisible, size divisible by P to the n, then the supernatural order at P is P to the infinity. Okay, and so you attach a supernatural number, which is like a natural number in that it's a formal product of prime powers, but then the super thing is that each one of the exponents could be infinity. They don't all, normally they're actual natural numbers and all but finitely many of them have to be 0. Here, they can be infinity rather than natural numbers, and infinitely many of them can be infinity. So like the supernatural order of Z hat, the profinite completion of Z, is product over all primes P to the infinity. If I take an infinite pro P group, then its supernatural order is P to the infinity. Okay, so you can make some statement here. So here, I'll leave you to think about the statement, but the statement of what kind of torsion module the, let me just say the Galois homology is going to depend upon the supernatural order of the Galois group. Okay. Yeah, I think this is a good place to stop. So are there any questions? Yeah, so again, you see that like I kind of didn't say, not only did I mean, I really was very disrespectful to this chapter. I spent one lecture where I was like, I'll tell you more interesting things about profinite groups than what Harari says in section 4.1. And then he goes on to say very important basic things about homology of profinite groups. And I was like, oh, these are great things. I'm not going to prove any of them, you know, see the book. But anyway, we want to get on with it. And again, I really offer to you guys, you could do a lecture on chapter 5. And let me tell you, it's really short. Let me find. So yeah, so it starts on page 79. And we hit exercises at the top of page 84. I'm not asking, it's not a lot here, right? So it's all very pleasant. You know, if you don't want to say Hochschild spectral sequence, then you don't have to. You know, you gotta get a free pass. All right, well, please think about it. And we're done for today, and back on Wednesday. And I think again on Wednesday, unless I change my mind, I really want to talk about Galois homology. So chapter 6. Oh, except maybe it uses a little bit of material. Anyway, we'll see. We'll see what I do. Okay. All right. See ya. Bye.